Modern AI agents face a systemic failure in state management. Without a persistent memory layer, autonomous systems exhibit severe context amnesia between sessions, resulting in hallucinations and catastrophic memory fragmentation. The industry's default response is to force-feed models increasingly massive context windows. Relying on transient context limits retention to a single session and guarantees the system forgets its own operational history the moment that session ends. The solution requires giving AI agents a canonical, persistent memory layer. This means implementing a durable, version-controlled knowledge base that acts as a deterministic runtime environment across all models and sessions. Obsidian provides the exact primitive needed for this architecture. In this paradigm, Obsidian operates as a headless file system where raw Markdown files execute as installed system capabilities. A stale note is a regression in the code, and an orphan file is dead logic. This dashboard illustrates the specific metrics validating this approach. The architecture we are examining is derived from a strict empirical analysis of 153 sources across 5 research depths, tested against a live fault containing over 4,750 files. The primary bottleneck preventing true agentic autonomy is the absence of a version-controlled deterministic state machine. Context windows scale token processing. Persistent file systems scale operational reasoning. Building this architecture introduces the plugin paradox. Every additional software dependency you install increases your maintenance surface and introduces a new vector for agent conflict. This bar chart compares the evaluation results of 23 standard Obsidian plugins tested for agent infrastructure. Only 3 survived the scrutiny checklist. The ecosystem is rich with tools, but the vast majority fail in an autonomous context. The surviving stack relies on local REST API and direct file system access. These tools expose vault operations over standard HTTP protocols, allowing agents to read, write, and search the system without requiring Obsidian's graphical user interface. Highly recommended AI-native plugins, including embedded chatbots and automated smart linkers, failed the evaluation. These plugins inject secondary orchestration surfaces into the software, which directly conflicts with the requirement that the system maintain a single, uncontested source of authority. The most robust multi-agent stack intentionally avoids brittle, over-engineered AI plugins. Reliable automation scales entirely on boring, standardized file primitives. Transforming raw Markdown into autonomous action requires a rigid architectural stack. Understanding this system requires isolating the exact boundary where operational state separates from permanent memory. The stack starts with the canonical Obsidian vault at the foundation. Built on top are 6 derived layers: recall for retrieval, governance for trust, freshness for aging, execution for processing, interface for interaction, and orchestration for planning. This stack operates under the strict single source of truth rule. Operational state, vector embeddings, and external dashboards stage information, but they must never leak back into the canonical memory layer. This matrix details the 5 specific trust states that govern how the system evaluates belief: working, canonical, contested, stale, and superseded. The architecture forces explicit visibility of uncertainty rather than allowing agents to make silent assumptions. The hierarchy of data is absolute. When staging databases, vector indexes, or operational queues disagree with the Markdown file system, the Markdown file system wins. The highest conviction failure uncovered during the depth research was the attempt to use Obsidian's native .base files as an agent query layer. Every proposed integration recorded a 0% pass rate. The contrarian view that killed this integration points to a simple fact. Proprietary YAML abstractions are designed entirely for rendering graphical dashboards for humans. They possess zero utility for agentic logic. These native visual tools enforce a permanent expressiveness ceiling. They operate exclusively on front matter and cannot perform SQL-style relational joins, cross-fault data aggregations, or full-body regex searches. This side-by-side comparison shows the correct architectural paradigm. A lightweight script using raw Python, DuckDB, or Pandas can query standard YAML front matter across thousands of files in milliseconds. Forcing autonomous agents to reverse engineer proprietary graphical UI abstractions introduces permanent fragility. Utilizing standardized global data protocols is mandatory for agent communication. The industry relies heavily on graph database traversal to execute context retrieval. This assumes that spatial relationships between documents always equate to conceptual relevance. This network map highlights when topology is useful. Graph analysis excels at identifying isolated dead code clusters, known as orphans, and surfacing highly linked central hubs via PageRank, an algorithm measuring structural importance based on incoming links. For generalized intelligence gathering, the architecture requires a 3-layer hybrid retrieval stack to achieve full contextual understanding, rather than relying on a single method. The first layer is semantic search, which handles broad, conceptual queries using pgvector. pgvector is an open-source extension for PostgreSQL that allows the database to store and search mathematical representations of text. The second layer is lexical search for precise technical lookups, utilizing BM25 via the REST API. BM25 is a standard ranking function used by search engines to evaluate the exact word overlap between a search query and a document. The final layer is topological navigation via NetworkX, which is reserved exclusively for genuinely structural and relational dependency analysis. NetworkX is a standard Python library used for creating, manipulating, and analyzing the structure of complex mathematical networks. Contextual assembly requires a multi-dimensional approach. The system must process a document's semantic meaning, its exact phrasing, and its structural position simultaneously to return a highly resolved answer. In a canonical vault containing over 4,700 files managed by multiple autonomous agents, epistemic drift is inevitable. A rule established in January will eventually collide with research ingested in March. This automated 4-step contradiction pipeline prevents conflicting logic. Step 1, delta detection, isolates recently modified files. Step 2, semantic prefilter, pulls the top 5 similar chunks. Step 3, NLI triage, uses a cross-encoder to score contradiction probability, dropping pairs below a 0.7 threshold. Step 4, executes LLM adjudication. A heavy language model is triggered only for the high-confidence flags, determining the severity of the conflict and outputting a final, logged judgment for the human operator. Without a bounded, automated pipeline for detecting logical contradictions, an AI operating system silently accumulates conflicting beliefs. Agents process opposing rule sets until the logic collides in a catastrophic runtime failure. The 7-layer architecture creates a compounding operational effect. Improvements applied to any single tier of the OS recursively strengthen the exact mechanisms driving the other tiers. Upgrading the embedding model yields superior contradiction detection. Catching more contradictions establishes stronger canonical trust in the vault. A highly trusted vault results in higher fidelity retrieval, decreasing the agent's reliance on external data. To protect this compounding loop, the system relies on doctrine tests. Every proposed infrastructure change must pass a strict evaluation criteria before it is deployed into the runtime environment. The rejection criteria are absolute. Any pull request or workflow change that adds recurring manual labor, creates a hidden secondary truth layer, or forces vendor lock-in is instantly denied. The long-term survival of an AI architecture depends entirely on its ability to actively resist unnecessary complexity. Infrastructure bloat destroys deterministic execution. Successful AI OS design is an exercise in operational restraint. It requires rejecting hypothetical scaling solutions and enforcing universally recognized data protocols across a flat file system. This restraint serves the system's foundational operating principle. The prime directive dictates that continuous automatic self-improvement is mandatory. The system today must be worse than the system tomorrow. An autonomous agent's actual utility scales with the rigor and determinism of its file system, regardless of the parameter count within its neural network.